Hi, in this video we're going to talk about maximums and minimums, and maximums and minimums fit into a broader topic called order statistics. So let me explain what order statistics is with an example. Let's say I have these observations. I see these, when I list out numbers like that, I'm thinking of these as observations from a random variable. And let's say these are my observations these are the 5 observations that I have. Well, the first thing that you do when you're talking about order statistics, first thing we do is we reorder the values in increasing order. So I'll just rewrite the values in increasing order. So I got a 3, 5, 5, 8, and 12 are the same values, just in increasing order. And then when I do that, the first value, the first number there, 3, is the first order statistic. The second number is the second order statistic. The third is the third, and so forth. Now notice that you can't have the second order statistic be the same as the third order statistic. And then of course I have the fourth and the fifth order statistics. And so generally you're going to have like n observations. So let's say that you have n observations from the random variable. You're going to have n order statistics. And so the notation, the standard notation that folks use is an x with a subscript of parentheses 1 as the first order statistic. But the first order statistic, as we just said, as we just kind of illustrated a little while ago, the first order statistic is just the minimum of all those observations. And then likewise, using similar notation, I have an x with a subscript of parentheses n. That would be the last or the nth order statistic, but the nth order statistic is going to be the maximum of the observations. Okay, so that's what the order statistics, broader range. You could actually talk about second order statistics and third order statistics and so forth, but we're only going to focus on the first and the last, the minimums and the maximums. And I'm going to change the notation a little bit to help me, with notation later on. So for the minimum, instead of the x with a subscript of parentheses 1, I'm just going to use an m to represent the minimum of those values. And then for the maximum, I'm going to use an m with a tilde on top to represent the maximum. Okay, so that's what you would do if you had values. Now, you could do this in a random process. Now, so notice these are just values. Everything's a value. And so, it doesn't make sense to talk about the probability that a value is greater than or less than some other number. If it's a value, it's just the probability that the value is greater than some other number is either a 1 if it is or a 0 if it's not. So it's not. So what we do is let's look at, instead of a value on a value basis, let's look at a random variable basis. So I'm going to change all of the lowercase letters there to capital letters. Now I'm thinking of random variables. So cap x of 1 is a random variable representing the first observation, the first of n observations when I just randomly choose an observation from a random variable. That's kind of how I'm thinking of that. And then notice I changed the lowercase m and m tilde to a capital M and m tilde because now the capital M is a random variable representing the minimum of all of those variables, and the cap M tilde is the random variable representing the maximum of all those cap x sub i's. And now I can talk about probabilities like, well, what's the probability that the minimum is less than or equal to 7, or the probability the minimum is greater than 183. I'm just making stuff up. The m here is minimum, so the first probability is the probability that cap m being less than or equal to 7. It's just saying what's the probability that the minimum of those n variables is less than or equal to 7. And again, I'm just making up numbers like 7, 183, and so forth. I can look at other probabilities involving maximums, the m tilde random variable like that. Let's focus on that first probability. I want to make an observation here, an important observation to help you complete problems like this. If we look at the event that cap m is less than or equal to 7, and I've got highlighted in red also that cap m is, again, the minimum of these variables. The question is, well, how could the minimum of n variables be less than or equal to 7? Well, it gets kind of complicated. The minimum could be less than or equal to 7. You could have the first one be less than or equal to 7, but not any of the other ones. Or you could have the first 2 be less than or equal to 7, but not any of the other ones. Or you could have the first and the third one be less than or equal to 7. Or you could have the last one be less than or equal to 7, but not any of the others. It gets to be a very convoluted, I'm calling that a convoluted or complicated event. On the other hand, if you look at the next probability, the event that I have highlighted here, that cap m is greater than 183, that's saying, well, what about the event that the minimum of these n variables is greater than 183? How could that happen? Well, if the minimum is going to be greater than 183, that says that the first value has to be greater than 183. Otherwise, the minimum's not going to be. If the first value was less than 183, then the minimum would be at most what that value is, which was less than 183. And so that won't satisfy the event that the minimum is greater than 183. So if the minimum is greater than 183, the first one has to be greater than 183. Not only that, we could use the same argument to say that and the second one has to be greater than 183, and the third one has to be greater than 183. So the only way that a minimum could be greater than 183 is if all of the cap x sub i's were greater than 183. So that's not a convoluted event at all. That's a simple event in the context. You can describe the event in one sentence, in just one simple sentence, that all of the cap x sub i's must be greater than 183. Okay, so now let's move on to maximums, and I'm going to let me highlight in green and blue these events that I'm taking the probability of with respect to the maximum. And I want you to pause the video for a second and decide which one of these events is a convoluted event and which one is not. And so the fact is that if you look at the first event in green, I'm going to change it to red because that's going to be the convoluted event, the maximum being greater than 100. How could the maximum of n variables be greater than 100? Well, there's a bunch of different things that could happen for that maximum to be greater than 100. You could have the first one be greater than 100, but not any of the others. Then the maximum would be the first one, which is greater than 100. Or you could have all but one of them be greater than 100, and that one that's not greater than 100 could have been the first one or the second one or the nth one. It's just a bunch of different convoluted events, sub-events that create this event that the maximum is greater than 100. On the other hand, if you look at the last probability and the event that the maximum is less than 1,000, how could the maximum of these n variables be less than 1,000? Well, the first one would have to be less than 1,000. Again, if the first one was not, then the maximum, if the first one was greater than 1,000, then the maximum would be greater than 1,000 because it would be at least as big as that first one. And so that's not the event that the maximum is less than 1,000 is not a convoluted event. Okay, so this is kind of the summary of this last discussion that we've had. The probabilities in red are probabilities associated to convoluted events. And the other thing I want to recognize is that if you look at the probabilities in red, that first probability involving the minimum is actually the cumulative distribution function of the random variable cap m, and then for the probability that cap m tilde is greater than or equal to 100, that convoluted event, well, that's actually the survival function. The event is actually the survival function of the maximum random variable. It's technically, let me make a quick comment here, is that I'm thinking of these as being continuous random variable. I'm thinking of the cap x's as being continuous random variables, and so I have the survival function there of cap m tilde. The survival function technically is the probability that the random variable cap m tilde is strictly greater than 100, but if in a continuous case, the greater than and greater than or equal to are not going to, the endpoint is not going to change the value of that probability. Okay, and so now if you look at the non-convoluted events, then the non-convoluted event associated with the minimum random variable is the survival function of the minimum random variable, and the non-convoluted event associated with the maximum random variable is the cumulative distribution function for the maximum random variable. And so the point here is that when you're working with probabilities, for probabilities involving the minimum, start with the survival function, whereas when you're looking for probabilities involving the maximum, start with the cumulative distribution function. So for instance, in that first probability, if I wanted the probability that cap m, that the minimum was less than or equal to 7, I would rewrite that, or I would compute that probability by computing the probability of the complementary event that cap M is greater than 7, and then just take 1 minus that, using the fact that probabilities of complementary events is summed to 1. Likewise, if you look at the M tilde is greater than 100 probability, that M tilde is greater than or equal to 100 is a convoluted event. So what I would start with is the probability that M tilde is less than or equal to 100. That's not a convoluted event. And then that's going to be an easier event to take a probability of, and then subtract that probability from 1. Okay, so let's look at, again, I want to talk about some other things that will make these calculations, these probability calculations, a little bit easier. And I want to do so by let's just focus on 2 events right now instead of generally n events. So let's look at 2 events. I think you'll be able to see how to extrapolate it. It's not hard to extrapolate what we're doing for 2 events to more than 2 events. So let's say that I have two random variables to extrapolate what we have for 2 random variables to more than 2 random variables. So let's say that I have cap M now is the minimum of these 2 random variables, and as we just mentioned, you want to look at survival function probabilities. You want to look at the survival function that's not a convoluted event. So let's look at, say, the probability that cap M is greater than some value x. And so how could cap M be greater than, how could the minimum of those two random variables be greater than x? Well, the first variable would have to be greater than x, and the second one would have to be greater than x in order for the minimum to be greater than x. So that's what this sentence says. And remember from the first module, the probability, this is just a probability of one event and another event. So I've highlighted the cap E1 to be the event that cap X1 is greater than x, and likewise the events in blue. And remember, the probability of cap E1 and cap E2 is generally a conditional probability times a marginal probability. But what would make this a whole lot easier is if we had independent events here, because then what I have as that, well, I'll highlight it in red. What I have as that conditional probability then becomes a marginal probability itself. It's just the probability that cap E of the event E1. And so that's going to make these calculations a lot easier. And so when we're in the situation of calculating maximums and minimums, we're going to assume that we have independent events. Now, the independent events means that is corresponding to saying that the random variables themselves are independent. So cap X1 and cap X2 are independent. And then in that case, it makes this probability that cap M is greater than x an easier probability. It's just the probability of it's a product of the probabilities that each one of them is greater. Each one of the random variables is greater than x. Okay, so now there's another assumption that we can make that makes the calculation even easier. And so that is the assumption that the random variables cap X1 and cap X2 are identically distributed to a common distribution that I'll call cap X. Now what that means is to say that these random variables are identically distributed to some random variable cap X. What that means is that anytime you're calculating a parameter with respect to the cap X of one random variable, you'll get the same value you'll get the same value if you calculate the parameter with respect to the random variable cap X sub 2. And all those values are going to be the same. For instance, in this case, I'm thinking of the parameter that I'm calculating to be the probability that cap X1 is greater than X. Well, again, identically distributed. It works for any parameter, and for this particular parameter, then I would get that probability would be the same as the probability that cap X2 is greater than X. And all of those are equal to the parameter that I would calculate, to the value of the parameter I would calculate with respect to the common distribution, the cap X random variable. And so what I have highlighted in red and green at the very bottom on the last row, each one of those probabilities is just the probability that cap X is greater than the value X, again, assuming that I have identically distributed random variables. And so I would just get as a value for this probability that cap M is greater than X, the value would be the square of the probability that cap X is greater than X, the common distribution cap X. And so, again, that's the assumptions that we're generally going to make in this context is that, well, first of all, that you're going to have independent random variables. That's actually listed in the syllabus, that you're expected to calculate maximums and minimums of independent random variables. You don't necessarily have to have that they're identically distributed, but it makes the calculations easier if you do. And if you combine these two, oftentimes in statistics, you combine those two statements to say that cap x1 and cap x2 are independent and identically distributed random variables. Almost always in statistics anyway, where they'll say it like this, but implied in this is, especially on the identically distributed part, is that there's a common distribution that you're using. So I would, to be more precise, they're independent and identically distributed to some common distribution that I've labeled cap x. But again, most of the time they'll leave off that very last part in red and just say that they're just identically distributed. Okay, so finally, let's look at what happens if instead of the minimum, looking at the minimum, the random variable representing the minimum, we look at the random variable representing the maximum. So that's the cap M tilde that I was talking about. And again, earlier in the video, I said if you're looking at the maximum random variable, then you want to start with the CDF, the cumulative distribution function. And so this is what we would get in this case, that the maximum, the only way that the maximum could be less than or equal to x we would have to have the first one be less than or equal to x and the second one be less than or equal to x. So that's what the probability in the bottom red is showing. And now using independence, I know that the probability of that and is just a product of the probabilities of each part. And then using the fact that I'm assuming, or using my assumption of identically distributed random variables, both of those probabilities are just equal to the probability that cap x is less than or equal to x. And so that's what I would get as my as my answer for this probability. Again, it should be pretty easy to extend this to more than two random variables that you're taking the minimum or maximum of. In fact, let me finish this video with an example. Let's say that I have a random sample of 10 observations from an exponential distribution with a mean of 1,000. So that random sample is collected, and I want the probability that the maximum of the observations is greater than 1,200. So first of all, I've got 10 observations, so I'm going to have 10 variables here. When you see the words random sample is indicating that you're in this IID framework. So these variables are independent and identically distributed, and implied in the sentence here, it tells me that there are observations from this exponential distribution with a mean of 1,000. So that's the common distribution that each of these random variables, the cap x1, the cap x2, all the way up to the cap x10, all of those are random variables, but they're all identically distributed. They're to that common distribution, cap x right here. And now let's use our notation. Cap M tilde is the maximum, is what I'm representing as the random variable. It's the random variable representing the maximum of those 10 of the 10 variables. And the problem here is asking me to calculate the probability that this maximum is greater than 1,200. Almost all the problems that you're going to see in this context, the probabilities they're going to ask you to calculate are the probabilities of the convoluted event. And so this is the convoluted event. So what I do is, again, I'm going to rewrite this, or I would compute this probability by computing 1 minus the probability that the maximum is less than or equal to 1,200. And I can calculate that by the only way the maximum could be less than or equal to 1,200 is if all of them are, each individual cap x sub I is less than or equal to 1,200. And then by independence, this probability of a sequence of ands is just going to be the product of the probabilities of that each one of them is going to be less than or equal to 1200. So that's by independence. And by the identically distributed part, each one of those parameters for each of those random variables is just equal to the probability that cap x, the common distribution, is less than or equal to 1200. And so I get this. So the question now boils down to being able to calculate the probability that cap x is less than or equal to 1200 when that cap x is the common distribution that's exponentially distributed with a theta equal to 1000. And so you got to go back, you got to know your facts about exponential distributions. This is the CDF for an exponential distribution, and I know that the CDF is 1 minus e raised to the, and then the negative 1.2. The 1.2 comes from the 1200 being divided by 1000. Again, go back and look at your facts with exponential distributions. And then I want to, my final step is let me complete the problem. That's not your answer. That's probably going to be one of the answer choices, and they're going to trick you if you don't remember to go back and finish the problem, which is the original problem was to calculate the probability in red. So my answer is actually 1 minus that probability in green. And I got, if I did the arithmetic right, I got like a 97.22% on that. I think it's also, before I finish, I think it's also a good idea to, on these problems, think about logically or intuitively, were you expecting a big number or a small number, or something like that. I mean, I've got 10 observations that are coming from an exponential distribution with a mean of 1000. So the average is I'm expecting on average to be given to select a 10 on average. I'm sorry, the mean was 1000. On average, I'm expecting to select a 1000 when I select an observation from that random variable. And I got 10 of them, and so then the question is, well, what's the probability that the maximum of those 10s is greater than 1200? So it's probably very likely that the maximum is going to be over 1200 when I go through this process. And so it is very likely, as you can see, because we just found out that the probability is actually a little over 97% there. Okay, so that does it for maximums and minimums, and I'll see you in the next video.